Okay, so we continue to discuss example 3.3.b. Okay. All right. All right, so we first establish a probability space Xn, Fn, and Pn. For this random experiment with a deck of n cards. Okay. All right. So as we described on Tuesday, that we shuffle this deck of n cards, right? And then we turned over a card one by one. And before turning over a card, a player will guess whether will make a guess or may not make a guess. If the player make a guess, the guess should be that the next card is card number 1. Okay, so that so the sample space Xn can be described by a pair of sequences or a pair of subjects. Okay, and the G represent the guess sequence, and the guess sequence will be represented. Okay, so 1 means that 1, 0, 0, 0. So 1 represents the player will make a guess. 0 means that the player will not make any guess. Okay, so that 1, 0, 0, 0 means that the player will make the guess before the first card is turned over. Okay, and the next one will be at the first time the player does not make any guess, but at the second time the player will make the guess. So that's 1. Up to all right. So this is that except that the last card, the player does not make any guess before. Okay, so 0, 0, 0. Right, and the sigma is a permutation of integers in this interval, because we index the n card by positive integers from 1 to n. Okay, so the sigma will describe the way the sequence that the card is turned over. Okay, so okay, so for example, okay, with n equal to 3, all right, then x will be G and sigma. such as G is in 1, 0, 0, 0, 1, 0, and the 0, 0, 1. And the sigma is in 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay? So that is example, right? Because that we permute integers 1 to 3. So there are 3 factorial ways to permute these 3 integers. So that is 6. Okay, that's 6. Any questions about the sample space? So the sample space is the set of all possible outcomes to describe these random experiments. So, and in general, the size of the sample space is n times the n factorial. Okay, because they are n possible guess sequence G, and they are n factorial possible sigmas permutations. Okay? Any questions? Okay, so if no questions, then because the sample space is a finite set, so a common selection for the sigma algebra would be the power set of X. Okay. All right. So now for n equal to 3, the event, the win event, so the win event, okay, so let's look at that. All right, so the win event is that, okay, if the guess sequence is 1, 0, 0, and then so the player wins when it's 1, 2, 3, okay, all right, or the other case is that 1, 3, 2, okay. So this is the guess sequence. This is the sigma, right? So if the player make the guess at the first time, and the player wins, if that card number 1 will be turned over at the first time. So that will be 1, 2, 3, or 1, 3, 2. Okay? There are 2 other possibilities. If the guess sequence is 0, 1, 0, then that would be this one, or okay. All right, and there are 2 more cases. 0, 0, 1. So it's 2, 3, 1. 0, 0, 1. 3, 2, 1. Okay. Any questions? All right. So now, we have Fn is n. Now the probability function Pn from the Fn to the set of all non-negative numbers. So the probability function will be dependent on the chosen strategy of making a guess. Okay? Okay, so I will explain why the probability function depends on the strategy of making a guess. Okay, but before there are some common properties of Pn, right, for this learning experiment. Okay, so let E sigma is the event that the n cards appear in the order as described in the permutation. Sigma, i.e., the event consists of all outcomes. As we know, outcome is just a pair of one guess sequence and one permutation. And the sigma is fixed. So the guess will be in this set. Right? So E sigma is okay, so we focus only on how the n cards turned over in n times. Okay, and the way is described by the permutation sigma here. And so for any of such a probability function, as we know, the probability of this event should be 1 over n factorial. Okay. Okay, because why? Because we shuffle the deck of n cards. Once we shuffle the deck, okay, then we will assume that the sequence of the card in the deck is completely random. Okay, and so the way when we turn cards over one by one, the order will not affect by any guessing strategy, right? That will not be affected by any guessing strategy, right? So okay, so that the probability, no matter what kind of probability function we will have, even though the probability function will be dependent on the choosing strategy of making a guess, even though that. But if we look at the order of cards appeared, then the probability of this event would be 1 over n factorial, so that they will be equally probable. Right? So that is something that is some property shared by all possible probability functions. The other invariant invariant property is that suppose G1 is the event, all right? G1 is the event that the player makes a guess at time 1. Okay, so G1 is this event, consists of all outcomes so that the guess sequence is fixed because that the player makes a guess at the first time, so it's 1 0 0 0 0. And the permutation, the sequence of the card appearing will be arbitrary. Okay, so G1 is this event. Now, so I think to make things clear, I put instead of putting 1 in the subscript, I put into the superscript there. Okay, so the conditional probability, okay, of this event that the n cards appear in the order described by the permutation sigma, given that the player make a guess at the first time, right? But remember, before the player make a guess at the first time, we haven't turned any cards over, right? Because we always make a guess, or decide not to make any guess before we turn a card over, right? So that the sequence actually will not be affected by this event. Okay. All right, and so this is the same as a complement. Okay, the complement of EG1 is that the player does not make any guess at the first time. Okay, so So this information will not affect the probability of the event. Okay. Okay, so that is the second invariant properties for any probability functions. Means that for any chosen strategy. All right? And so if H is any event, okay? So if H is any event concerning with only how the N cards turn over, i.e. H is a disjoint union of E sigma. Okay. Then P and H given G1. Okay. And this is actually the summation of E sigma contained in H of probability in G1, and this is so this is probability of E. Okay, and this is equal to the Pn H given E on complement. So this is a consequence of this property. Okay. And here, H is the disjoint union. Okay. All right. Now I would illustrate that quite different strategy of making a guess or change the probability function. Okay. All right. So suppose. Consider n equals 3. All right, so strategy. Number 1, that always make a guess okay, at time 2. All right? So that is the first strategy. Always make a guess at time 2. Now, in this strategy, okay, so the P3 of 1, 0, because that always make a guess at time 2. Oh, I'm sorry. So possible outcome, I mean, the possible outcomes means that an atomic event has positive probability would be with the guess sequence which is equal to 0, 1, 0. Okay, so that this atomic event will be 1 over the 3 factorial. Zero, 1, 0. Sorry. And 1, 3, 2. It's 1 over 3 factorial. Yep. Okay. You see, I will explain after I write down everything. Okay. Three, 1, 2. Three, 2, 1. And okay, right. Because we have it's 3. I'm sorry, I forgot to put. In here, we have 3 times 6 is 18, right? So we have 18 possible outcomes. Now, and out of the 18 possible outcomes, these 6 possible outcomes can have positive probability. But the other 12 outcomes will never appear. Why? Because of the guessing strategies, you always make a guess at time 2. Right? This is your strategy. So the probability for others, so for with G equal to 1, 0, 0, or 0, 0, 1, right? So if G is 1, 0, 0 or 0, 1, never appear. So the probability is 0. Okay? And as we described, it is sufficient to assign probability for atomic events, right? And now we have 18 atomic events. So we assign probability for 18 atomic events. And for 12 atomic events, the probability will be 0 because the strategy you choose. Now, here. So the possibility will be only just 6 possible outcomes. All right? Now, and because you have already decided you will make a guess at the second time. So the only randomness, where is the only randomness? It is the permutation of the 3 cards, right? And so, but you shuffle the cards, right? Randomly. So the order for the 3 cards to appear will be equally likely. And that's why we have 3 factorial, because we have 3 factorial possible permutations of 3 cards. So that is the reason why I put 1 over the 3 factorial. Is that okay? All right, so this probability measure, this probability function, it's determined by this strategy. Yeah. Okay, so this is the probability measure. Now you have one. Okay, and so with this strategy, you have the probability space established. Now, what is the probability for this strategy? So for this strategy, we have already established a probability space already, right? And so what is the probability of the win? So the win probability okay? So now the win probability, so look at here. The probability for this atomic outcome is 0, right? So this is the probability of, we know we have because it's this event is the union of 1, 2, 3, 4, 6 atomic events, and they are disjoint unions, right? So that so this is so let me write down it. So this is 1, 0, 0, 1, 2, 3, okay, plus, so this is atomic event, Okay? Now, for this probability functions, so we know this is 0. This is 0. And these two, we have 1 factorial. Okay? Plus 0, plus 0. Okay? Because the guess sequence, this 0, 0, 1, 1, 0, 0, never occur. Never. Okay, so that is 1 over n. And remember, we want to prove a strong result that the win probability is always 1 over n, no matter which strategy you will choose. Okay. Strategy number 2. So that is strategy number 1, right? Now we consider strategy number 2. Make a guess after car 1 appears, or if card 1 does not show up before the last chance. Make a guess. It seems naive. It says that, okay, let me okay, so the strategy is that when card number 1 appeared, so the player will not make any guess, right? Until card number 1 appeared, then next time the player will make a guess. So never success, right? That is foolish, but anyway, so you can see this is a very foolish strategy. But there is one more chance. If card number 1 does not show up before the last chance, then the player make a guess. Of course, right? Because before the last card, the card number 1 never appeared before, then for sure the remaining card should be card number 1. So that the player make a guess. Right? So that is a kind of silly, right? A silly strategy. Right? And so with this silly strategy, what is the probability function we have? Okay? So then Pn, and this time we describe the okay? So the player never make a guess at the first time. Why? Because no card appeared, right? Before the first card. Right? So now the player will make guess at the second time. Why? Because the card number 1 has appeared at the first time already. Okay, so this is the card. This is the sequence for the 3 card appears. The first time is card number 1. The second time turns over is card number 2. The third time, card number 3 will be turned over. Okay. Now, because that the player see that the card number 1 has been turned over at the first time, so he make the guess at the second time immediately. Okay, so that is the story here. Okay, and so this outcome will appear, means that it will show up with positive probability. Okay, and so for this one, so what is that? So this is 1 over the factorial, and I will explain that later. Why? P3, sorry. Now n is 3. 0, 1, 0, when 1, 3, 2. All right, and 0, 0, 1, and 2, 1, 3. All right, so now, because count number 1 appeared at the second time, so that the player will make a guess at the third time. Okay. This is the same situation. All right. Here, the card appeared in the sequence 2 and 3. So card number 1 haven't appeared until the last one. So the player will make the guess at that time, of course, right? And so this is 1, 2. Okay, and the probability of is 0 for all other outcome. Okay, so they are all outcomes. So you compare with this probability with that, they are different, right? They are different. For example, this atomic event for 32, that for this atomic event the probability is 1/6, but in here the probability is 0. Oh no, I'm sorry, not this one. Okay, I should say this one. Okay. And this atomic event is 1/6, but in here is 0. I'm sorry. So these two probability functions are different. So they are different. Okay, they are different. And for this measure, the win probability, according to the same as that. So let's see. This one has 0 probability. This is 0 probability. How about this one? This is 0 probability. This is also the 0 probability. But these two has 1/6. Over N2. All right, let me demonstrate a third strategy. By the way, any questions about the first two strategies. Okay. Now, third strategy. Number 3. Toss a fair coin to decide whether or not to make a guess at each time. Okay, if no guess is made before, and if no guess is made before the last chance, make a guess. All right, so now the player decide to use a coin, a fair coin, all right, to see if the face of the coin is head, then the player will make a guess. If the face of the coin is a tail, then the player will not make a guess. And because that the coin is fair, so the coin will turn a head or a tail with equal probability. That would be 50%, right? Okay, so with this strategy, so the P3, now we describe the atomic event, right? So 100, okay? 100 means that the coin, when the player toss the coin for the first time, the face of the coin is head, right? So the player will make a guess at the first time. And the sigma, so the sequence can be, right? So that will be 3 factorial times 1/2. Okay? One over the 3 factorial is that is here, as we know that the card is in the order described by the permutation sigma. Right? They will not be affected by the strategy, right, of making guess. Okay. But this guessing sequence depends on the way the turns out of tossing a coin. All right. So that is this one. And the P3 0, 1, 0 sigma. So that would be 3 factorial times. So that means that the first tossing a coin is a tail. The second tossing the coin is a head. Okay, and so that the model is that we have half probability, Okay, so we think about that they are in this way. And P3, 0, 0, 1. 0, 0 means that the first tossing and the second tossing of the coin render the tails, two tails. Okay, so that for the last chance, is because this is the last chance, so the player will make a guess. Okay, so it's a sigma. So this is 3 factorial times. Okay. All right, and so you can see all 18 atomic events has a positive probabilities. Right? Because this describes 6 possible, because there are 6 possible sigmas there. Okay? And the total probability, so the summation, so the probability of, okay? The probability of that is summation of all possible sigma, P3. You can check. Sigma. Okay. So we sum over all 16 possible atomic events. And so this is 3 factorial times 1 over 3 factorial times over okay, and you check 1/2, 1/4, 1/4, and this is 1. We have done. So the total probability is equal to 1. Okay, so now you have this. Now this probability function quite different from the last two, right? So we have a third one. Now, under what is the winning probability under this strategy? Okay, so this strategy is probabilistic strategy. Unlike the last two strategies are deterministic, right? There's no randomness for the strategy. But for this strategy, it's a probabilistic strategy. Okay, and so the probability of win, once again, so we have to sum over the probability of 3 atomic events here. All right, so this is 1, 0, 0. We have 2, 1, 0, 0, 2, 0, 1, 0, and 2, 0, 0, 1. Okay, so what is that? We have 2 chances. Is that okay? Okay, and so that is 1, 2 chance, chance. Okay, and this is again 1 over n. So once again, we have 1 over n. Okay, so so now I have demonstrated 3 different kind of strategies, and each strategy corresponding to different probability functions, right? So we have established different probability space for the running experiment corresponding to 3 different strategies of making a guess. But you can see they have the same win probability, which is 1 over 3, 1 over 3. Okay. So let's take a break for 5 minutes, and I will show that by induction that that this is true for arbitrary n, not only for n equal to 3. Okay, right? All right. Okay, so our goal is to prove that the win probability is, is 1 over n if we have a deck of n cards. All right. So basically, we will prove that by induction. For n equal to 1, there is only one card. Only one card, and the card is indexed by 1. So the winning, I think any player will say next card is 1 because there is only possible one cards. Okay, so the probability of 1 win is 1, and this is 1 over n. Okay, and n equal to k. So we assume that the statement is true, right? So if k equal to k, n equal to k, the statement is true. Means that if we have a deck of k cards, then the winning probability okay. Now, we let n equal to k plus 1. Okay, so now the p k plus 1 of win becomes to p k plus 1 of g1. So by, let me say, by the decomposition formula, okay, we know that P win is equal to P of G1, I'm sorry, Pk plus 1, given Pk plus 1 of win, but it's G1 plus Pk plus 1 of G1 complement times Pk plus 1 win event G1 complement. Okay. Is there any questions? So as we see, so this is the win event. This is the sample space, k plus 1. Okay, and we decompose that. So this is G1, this is G1 complement. Okay, and so the win probability with a deck of K+1 cards, right? It's a sum of two terms here. Okay. Now we will compute these two conditional probability. Any questions? Right? No questions. So, all right. So so now Pk+1 of win given G1. All right, so this is Pk+1. Now, at the first time, the player make a guess, and the result is that the player wins. So that means that this is saying that the first card of the deck is 1 given G. Okay? Oh, sorry, G1. So the first card of the deck is 1. All right, and remember, that means that it's an edge, right? It's an event. So this is an event. Concerning to concerning to I'm saying that concerning with only how the N cards how the K+1 cards turn over, right? So it's a kind of edge event we described before. And so this is probability of K+1. So the first card of the deck is 1, right? Because that is this conditional probability is the same as unconditional one, because that this event, this action will not affect the first card of the deck is 1. But the first card of the deck is 1, which is equal to 1 over K+1. Okay, because that we have K+1 cards, and the permutation that the first card of the deck is number 1 card will be 1 over K+1. Okay. Now Pk+1 win the G1 complement. Okay. So this is Pk+1. The first card of the deck is not card 1, and the player wins given G1 complement. Okay. Is okay? So the first card of the deck is not card 1. Otherwise, if the first card of the deck is card 1, and the player does not make any guess at the first time, then the result, the player will lose. Okay, but we are talking about the win. So this event is actually equal to this one. All right, and so this is the P, K plus 1. That's the first card of the deck is not card 1. Condition on G1 complement times K plus 1. The player wins given that the first card of the deck is not card 1, and we have G1 complement. Okay, right. Okay, so in here, you know, the first, this is the event, and here. So and means intersection. So we are using a formula, probability of and I will examine this identity before, because that in here, as we know, conditional probability actually is a probability function. Okay, so it will satisfy the three axioms, and so you can see without conditioning. Okay, we have without conditioning on W. Okay, we have the formula that the probability of the intersection of E and F is equal to probability of E times probability of F given E, right? That is the formula in the last section. Okay, but when we condition the W of the event, then we have this similar property. Okay, so that is the case here. Now, for this one, so this is P, K plus 1. The first card of the deck is not card 1, right? Given G1 complement, right? Because that and because this event is an event again, is an event concerning with only how the k plus 1 cards turn over. Okay, so that we can eliminate the conditioning. Okay. Now, how about this condition probability? Okay, so that this condition probability is that the player does not make any guess at the first time. And we know the first card turned over is not card 1. It's other cards. Okay, and so that card 1 will be in the remaining k cards. Because the first card is not card 1. And we have k plus 1 cards. So card 1 will be in the rest k cards. And then the player wins. So the situation is similar to PK, and we have win. All right? So it's just like we have k cards in the deck. In the k cards, we have a number 1 card inside. Okay? And then the following, because that the PK will, and the probability, this probability function is induced by the guessing strategies. Okay, the guessing strategies and corresponding to the original guessing strategies, as well as that the first card, the first guess, the player will not make the first guess. So that will be the PK and the player win here. So this is the winning probability in the case that we have a deck of k cards. Okay, so this is the by. So this one give us by analogy. Okay. All right. Now the first one is k over k plus 1, because the first card turned over is not card 1. Okay, so it will be maybe card 2 up to card k plus 1. So you have this probabilities. And the PK win, and by our induction step, this is 1 over k. So that is 1 over k plus 1. Okay. All right, and finally, so we have proved that, we have shown that this probability is equal to 1 over k plus 1. And this probability is also equal to 1 over k plus 1. All right, so p k plus 1 of win is equal to p k plus 1 of g1 times 1 over k plus 1 plus p sub k plus 1 g1 complement times 1 over k plus 1. So this is 1 over k plus 1. P G1 plus P G1 complement. So this is k plus 1, 1 over k plus 1. Okay? All right? So by induction, on n, we have Pn win equal to 1 over n for all n greater than or equal to 1. And this is the end of the proof. questions? Okay. Right, so it is a long example because I analyze this problem in some depth, okay, by showing you more details. Okay, so this is an example for an application of the decomposition formula. Okay, and from the decomposition formula, now I will state the simple Bayes formula. Okay, is that all right? Suppose we want to find this conditional probability. This is the probability, the conditional probability of event F given event E has occurred. But in some situation, this conditional probability is hard to find it. So we will do it the other way. Now we know by definition, okay, so we have that. And now, by decomposition formula, this is PF, PE given F, plus P, F complement, PE given F complement. And this is called the Bayes formula. And the formula is useful when it is easy to have these two condition expectations. Means that it's easy to find the condition expectation of event E given whether or not event F have occurred. So these two. And also, it will be easy to find the probability of the event F and the probability of the complement of event F. Okay. All right. All right. So let's make an example to show how the Bayes formula used. Okay, so the random experiment a student is to answer a question of multiple choices. All right. On a multiple choice test. Okay. This is a simple test, maybe a question only. Okay. And so there are some prior information. a prior okay. One, little p is the probability of the event k that the student knows the answer. Okay, so knows the answer. So that is a prior information. The second, the student will randomly select one out of the m choices when guessing. Means that when the student does not know the answer. Yeah, for me, yeah, I did a lot of tests before when I was a young student, and whenever, as everybody knows, if whenever you don't know the answer, just make a random guess, right? So that is typical, right? Okay, so this is a prior information consists of two parts there. Okay, so now for the question. All right, so let C be the event that the student answer the question correctly. Right? So now, so what is the conditional probability that the student knows the answer, given that the student answered the question correctly. Okay. All right. So now this conditional probability is a little bit harder to find. So we will use with base formula. We have, so this is probability of that K intersect with C. Okay. And oh, by the way, I will replace this as probability of F probability of E even F. I'm sorry. So we have a probability of K, probability of C given K, probability of K, probability of C given K, plus probability of K complement, probability of C given K complement here. Okay, and probability of K, by applying information, probability of the event K is little p here. And because the student knows the answer, so of course, the conditional probability should be 1. Right? Because the student knows the answer, so that if the student knows the answer, of course the student will answer the question correctly, right? And for here we have p times 1. Now, K complement means that the student does not know the answer, so the probability is 1 minus little p. And if the student does not know the answer, right, the student he will guess, and the student will randomly select one out of the m choices. So the correct probability would be 1 over m. Okay. Right. And so that it would be mp 1 plus m minus 1 p. Yeah. Okay, and so if m is 5, so there are, the question has 5 choices, and the probability of p is 1/2. So half of the students know the answer of the question. Okay, then P of K, C. So this condition probability would be 5/6. So that is pretty high. Okay. Right? And an exercise is that so please establish a probability space SFP for this random experiment. And express the events K and the C as subset of the sum space. Okay? So basically I did not establish a probability space first for this random experiment. I just use prior information here, okay, to solve the problem. Okay. But it will be interesting that if you can establish a probability space for this problem. It's not complicated at all, okay? But it will give you solid inside. Why all this stuff work? Okay. All right, and especially express the events K and C as subsets of outcomes. Okay. Any questions about this example? Okay. All right. So so next Monday is a holiday, and we will know quiz or recitation class. All right. And by the way, next, not the coming Saturday, next Saturday, March 5th, I will have complementary lectures, because that I think I will arrange 3 complementary lectures on 3 Saturdays this semester. The reason is that I have to leave the country in the 15th weeks, okay, of the semester. So that I have to make up the lectures before I leave the country. All right, and so I will make the schedule for you. All right, if you can't come, that because we have a live streaming video on the YouTube, so you can watch the YouTube. But I really hope you can attend the class in the Saturday. Okay, right? So I will make you know the 3 Saturdays, and please reserve the times for me. All right, so have a happy holiday, and I'll see you next Tuesday.